Hi. So we're in Alexandra Canyon right here. So Alexandra Canyon is a provincial park. It's actually quite a popular tourist destination. There's an old bridge for Highway 1 right up above me right here. And we stop here to look at the morphology of canyons. So this is a really great example of a canyon that has an alluvial section upstream from here. And then we come downstream and we have a bedrock section all the way through here. And then if you look even further downstream beyond the new Highway 1 bridge, you can see that the river becomes alluvial again. So it is an alluvial canyon, alluvial sequence. So this canyon and all canyons tend to have really low width to depth ratios. Alluvial rivers have really large width to depth ratios. Canyons tend to have really small width to depth ratios. This canyon is really quite deeply incised as well. And by deeply incised, I mean it is incised within the valley and has these really steep, almost vertical walls on either side of the river. Another interesting thing about Alexandra Canyon is that it is a really good example of what we refer to as a constriction pool widening sequence. So looking upstream from here, we have a wider alluvial channel. It then comes into a lateral constriction. Associated with that lateral constriction is a deeply scoured pool. And so there is a pool right here in front of us that is about 35 meters deep at low flow and about 45 meters deep at moderate flows. And if you can believe it, the flow actually comes up to about the black line there at high flows every year, which is probably another 10 to 12 meters, which means that this pool can be as much as 60 meters deep at high flows. We have done a number of measurements in this canyon right here and found that there is a fair bit of alluviation in the canyon. So that means we have a bedrock canyon. It has rock on either side and a rock bed, but at low flows it alluviates. It essentially fills up with sediment. And so we have found that even at moderate flows, the sediment is evacuated from this canyon and it scours down as much as 10 meters before it hits the bedrock again. So we have this pool that essentially fills up with sediment and then is evacuated as soon as the flows start going up towards about half the mean annual peak flow. That means at high flows, the canyon is essentially free of sediment, but at low flows, it is covered by sediment.
Okay, so the circle of sediment elevation that Jeremy has mentioned has an influence of the bedrock erosion processes, and so the sediment can be used as a tool to erode the bedrock, and also at the same time, if you have too much sediment, you're going to cover the bed so that there will be no erosion left. So that's what we call tool and cover effect. So that means you have to have an intermediate sediment supply rate so that you have enough tools, and at the same time you also have enough bedrock exposure on the bed to erode the bed vertically. However, if you have too much sediment and when the bed is fully covered, the sediment can be deflected vertically to erode the walls laterally. At the same time, there's no vertical erosion left. So basically, in a low sediment supply environment, you have enough tools. At the same time, you don't have a lot of elevation. The bedrock can be eroded vertically. And in a high sediment supply environment, you have a lot of elevation on the bed, so that the walls can be eroded by the deflection or by the particles by the elevation.
So Alexandra Canyon's a really great example of one of these plunging flows or velocity inversions that I've talked about, where there's high velocity fluid down near the bed in a pool and slower moving velocity up near the surface of the river. So as we come into Alexandra Canyon right here, there is a pool that starts about 100 meters upstream of the bridge that we're standing on right now. The flow then begins to plunge down along the bed into that pool. The pool is at its deepest right underneath the bridge right here. And then if you look downstream, we start coming out of the pool. And as we come out of that pool, what we find is that the flow that went down in the beginning of the pool goes down in the bottom of the pool. That flow has to come back up again, right? You're going to push water down, it's got to come up. And the way that it comes back up in these canyons is it comes back up along the canyon walls as these massive boils that emerge on the surface of the river. And so we have these plunging flows bringing high velocity fluid down along the bed. Then that high velocity fluid has to come back up again. And it does when the flow starts exiting the pools, and it comes up as these large-scale boils. That means that we have lateral flow going on. So if we have flow going along the boundary and then it's coming up on the sides of the river as these big boils, that means we're driving flow into the sides of the river. And we're driving flow into the sides of the river, we're encouraging bedload transport to be driven into the walls. And that enhances the effect, the tools and cover effect, whereby we have deflected particles going into the walls when we have really high sediment supply rates. Now this canyon, like many of the other canyons that we look at, has a deeply scoured pool and a constriction which causes a plunging flow or a velocity inversion, where we have really high velocity fluid at the bottom of the river and slower moving fluid up at the surface. And that generates really high shear stresses on the bottom of the river, which makes it possible to carry very large sediment. So this canyon in particular, we have done calculations and when figured out that the canyon can move boulders even at moderate flow. So it can carry as bed loads through here boulder-sized sediment. At somewhat higher flows, we have done calculations that show you can suspend sand, you can suspend the gravel, but you can also begin to suspend small cobbles in this river. So that means you're able to carry cobbles up above the bed in the water column, which is really quite astounding. And so you can imagine when you go to the really high flows, what happens to sediment. You're really carrying very, very large sediment, essentially in a slurry down near the bed. That causes a lot of impacts of the sediment on the boundary. And as that is impacting the bed, you can actually feel the canyon shake. There's a lot of energy that is transferred from that moving sediment to the bed of the canyon and the walls of the canyon, which cause erosion.